Hi, my name is Cooper. I'm a math teacher and a data scientist, and I love to talk about math and statistics. Variables. We've all seen them before in algebra. There are x's and y's and z's, and they always represent some missing number that we have to solve for using our amazing math skills. However, in the context of statistics, when we're talking about variables, things get a little deeper. Different types of variables can have different meanings. In this video, we'll talk about a few different types of variables, what they mean or represent, and a few examples of them in action. The word variable gets thrown around a lot in our math classes, and in statistics, it still means pretty much the same thing that we're used to. A variable is just a representation of some unknown number or value. The biggest difference is that in other disciplines like algebra, you might be used to trying to solve for a variable, and there might only be one or a handful of possible solutions. Statistics is different. Variables usually represent measurements and can take on many different values, depending on the result of the trial, experiment, or whatever it is you're measuring. You're bound to hear about dependent and independent variables, as well as random variables. Let's take a look. Oftentimes, we want to know if there is a relationship or correlation between two variables. Perhaps we want to know if the number of hours students study for a test is correlated with better scores. Maybe we want to see if income is correlated with health in a specific area. Now, it's very possible that two variables might be correlated, but it doesn't necessarily mean that one variable is the cause of the other variable. Over the course of a year, we might notice a positive correlation between the number of people stung by jellyfish and the total sales of an ice cream truck. A positive correlation simply means that both variables are seen to increase and decrease together. As one goes up, so does the other. A negative correlation would be the opposite. As one variable increases, the other goes down. Back to our jellyfish. They appear to be positively correlated. However, one measurement is not necessarily the cause of the other, but rather there is most likely a third variable that is the cause of both. The temperature. When it gets warm out in the summer, more people go to the beach, and more people are buying ice cream. Now, it's true that correlation does not necessarily imply causation, but depending on the data being studied, we often do expect a certain level of causation. We probably assume that studying more hours will lead to students scoring better on an exam. But we won't have any data if this is true until we collect and analyze some. Since we suspect that the number of hours we study is causing the changes in the scores students get, we would say that the scores depend on the hours studied. Therefore, the exam scores would be considered, in this case, the dependent variable. Dependent variables are almost always plotted on the y-axis. This leaves the number of hours studied to be the independent variable. Its value does not rely on the other variable at all. It is independent. You might study more hours because you are more studious or because you have more free time, but you don't study more because you got a better score on the test. You haven't even taken it yet. That just doesn't make any sense. It's not always easy to distinguish between the independent and dependent variables, and sometimes it's just up to you to decide which one to plot on the x-axis and which one to plot on the y-axis. The other type of variable you might hear about in statistics is a random variable. A random variable just represents the outcome of a random process, like flipping a coin, or rolling a die, or measuring the height of a person you find on the street. And there are two kinds of random variables that we commonly work with: discrete, also known as qualitative, and continuous, otherwise known as quantitative. Discrete, or qualitative random variables can only take on one of several categorical values, aka qualities, like the flip of a coin, for example. It can only be one of two values, heads or tails. The same is true for the roll of a six-sided die. Even though the result is always a number, there is still a discrete random variable here, since the result of a roll can only be one of 6 integer values. Continuous random variables, on the other hand, can take on any real number value or quantity, like the height of a person. We might only round off their height to the nearest inch or centimeter, but theoretically, that person's height could be any decimal if we wanted to get precise with our measurements. A lot of times, discrete variables are different categories, something like colors or plant species, or anything that can be categorized with word descriptions. Continuous random variables are always numbers, and usually decimals rounded off to the nearest handful of digits. But be careful. Just because the data looks like numbers doesn't mean it's a continuous random variable. Like rolling a die, you might still be looking at numerical data. But if there are only a distinct number of possible outcomes and not a continuum of real numbered possibilities, then it's still categorical and discrete. Variable is a word with special meaning in mathematics, and this is especially true when it comes to statistics. When we're discussing correlation between measurements, as well as cause and effect between them, we often refer to the independent and dependent variables. You might also hear these variables described as the explanatory and response variables. In the same way that the dependent variable depends on the independent variable, the response variable responds to the explanatory one. The x-axis is where we plot the independent or explanatory variable, and the y-axis is where we plot the dependent or response variable. Random variables, on the other hand, correspond to representations of the outcome of random events. Discrete or qualitative random variables can only be one of a finite set of possible outcomes. Continuous or quantitative random variables can take on any real number value, even if they're often rounded off. And now, you're able to distinguish all different kinds of variables on your statistical journey.